This lesson is for Mrs. Cucci's College Now Pre-Calculus class. Today we're going to be talking about vector operations. We are on lesson 7.3. Okay, so today what you should be able to do by the end of this lesson is you should be able to perform calculations with vectors in component form, express a vector as a linear combination of unit vectors, express a vector in terms of its magnitude and its direction, and find the angle between two vectors using the dot product. And lastly, solve applied problems involving forces in equilibrium. Okay, so the first thing we need to talk about is something called position vectors. Okay, so first we're going to consider some vector v. And remember, when we're dealing with the vectors, our vectors are actually, when we write them, the v is like bolded. Okay, so we've got some vector v, and its initial point is the origin in the xy coordinate system, and a terminal point AB. Okay, so we say that the vector is in standard position, and we refer to its position as a position vector. Okay, so let's say I have my vector v, and it's written in component form. Component A is scalar, okay, and it's the horizontal component. By scalar, what I mean is it's a numerical quantity, okay, rather than a vector quantity. Now, B is also scalar, so it's a numerical quantity, okay, but it's your vertical component. So what this might look like graphically, so let's say I'm on my xy coordinate. Okay. And my vector may look like this. Remember, it's going from the origin. Okay. And of course, this being the distance along the x, and this being the distance up the y. Okay. Oops, sorry, this should be here and here. My apologies. Okay, so when we're talking about component form of a vector, okay, component form of vector AC with A equal to the point x1, y1, and C equal to the point x2, y2 is going to be vector AC. So this is how we put this into component form. x2 minus x1, y2 minus y1. Okay, so essentially you're finding the change in the x-coordinates and the change in the y-coordinates, and that gives you component form. All right, so let's try this first example. Okay, so we're going to find the component form of vector CF if, oops, C is equal to -4, -3, and F is equal to 1, 5. Okay, so again, we're simply using this form here. Okay, graphically what this would look like is if we have CF to begin, -4, -3, and F is 1, 5. Okay, so here's what my vector actually looks like. So what we're going to do now is we're going to take this and we're going to put it into component form. So CF, we've got 1, there's your x2, minus x1, and y2 minus y1. So the vector CF becomes 5, 8. Okay, so how you would draw that vector, remember we go from the origin. You're going to go over 5, and up 8. And from the origin, you draw your vector. Okay, so this would be your vector. And there we have it. Okay, so the next thing we're going to talk about is how we go about finding the length of a vector. Okay, so we're going to take a peek at that next. Okay, so another word for length is going to be magnitude. So the length or magnitude of a vector V is going to be equal to V1, V2 of that vector is given by, and so here's what we're going to use. So V equals square root of V sub 1 squared plus V sub 2 squared. Okay, so let's look at an example of that. We want to find the magnitude of vector V 5, 8. Okay, so we're going to use our formula here. We got the square root of V sub 1, which is going to be our 5, V sub 2, which is going to be our 8. So we get 25 plus 64, which is 89. So the square root of 89 is the magnitude of the vector, okay, or the length of the vector. Two vectors are equivalent if they have the same magnitude and the same direction. So that's very important, okay? Two vectors are equivalent if they have the same magnitude, same direction. So two vectors are equivalent if they have the same magnitude and direction. Okay, so if you're asked to prove that two vectors are equivalent, you're going to have to find the magnitude and the direction to show that they're the same. Okay, so kind of piggybacking off of that, Let's talk about equivalent vectors. All right, so what we're going to do is we're going to let u, vector u, be equal to u sub 1 and u sub 2. And we'll say vector v is equal to v1, v2. So then what we have to show for u1, u2 to be equal to vector v1, v2. If and only if, that's that double F, that means if and only if, u sub 1 has to be the same as v sub 1, and u sub 2 has to be the same as v sub 2. Okay, so we're going to stop there for today, and we'll pick up on operations of vectors in the next lesson. I think this lesson is going to span 3 days. All right, so make sure that you come prepared with any questions that you might have, and I will see you all tomorrow. Bye.